Hello students, Guillaume here with another video about programming. But this one, not about Excel, about R. So we focus on Excel thus far because I think it's quite important and most likely you're going to use it in other courses, most likely you're going to use it in the workforce. R is a completely separate software and it has different strengths. And here, just with a bit of time we spend, I want to showcase a few interesting things you can do with R. Now, I know you already learned it in your stats course, so that's very good. So here, it's not really a R course I'm going to do because we don't have too much time. I just want to focus on a few applications, specifically in the context of our course. And I don't think there should be too much repetition with what you saw in stats. I think I want to explain a couple of things specific to us. All that said, let me jump into R and let's get started. So here again, I know you've already had an exposure to R, so I'm not going to explain the environment of R Studio because you would have seen it before. So I'm going to jump right into the script. But if you have troubles with maybe installing R Studio or things like that, you can always flag them on the discussion forum. So just recall here on the top, I have my script. So those are R commands. When I execute them, they're going to appear here in what's called the console. Okay, and also on the right, there's a empty window here where possible plots are gonna appear. So first thing I want to cover is just the basic syntax. So I suppose this is a review, but R is called what we might call a vectorized language. So the main data structure in R is the vector or vector. What do I mean by that? Well, if you type square root of 4, of course, this is just a number, so it's going to return 2 here in the console. But R operates on vectors naturally. Okay, so if I declare an object that's not a single number, but now a vector, and you can do this with the function C. So here my vec would be a new object in R that I declare myself. I give it the specific name my vec. This is now a vector. Okay, so if I type, so here, careful that, whoops, this is the assignment operation. Okay, this arrow here. So now I have created my vec. I have assigned to my vec those specific values, but I don't see anything because I haven't displayed it. Okay, but if I type my vec, then I'm going to see the result, which is simply all those numbers. Okay, so it's a vector of numbers, meaning a sequence of numbers in that specific order, 6, 5, 4, 3, 2. Now, when I say R is vectorized, it means I can one shot make an operation on all the elements of the vector. For example, the function square root that we used before on one number, I can use it on a vector. So if I here I'm using the shortcut Control Enter. When you select something, then you do Control Enter. It's going to apply it. It's going to launch the operation and apply it. And sorry, execute it in the console. So here you see it has applied the function square root to all the numbers in my vector. To assess specific elements in a vector, you need to use the syntax square brackets. Okay, so my vec is still my vector from before, but square brackets 3 would mean it would grab one single element in this vector, the third element in this instance. Okay, so if I launch this, you see my vec bracket 3 would be 4. Well, yes, because 1, 2, 3, the third element in my vector is 4. Of course, if you do this, my vec, the fifth, say, that would be 2, and that's it. Okay, if I do 6, it's going to be an NA because there's no sixth element in that vector. Just know that this works as well with the square root my vec. Square root my vec is itself a vector. Okay, so it's a sequence of number being the square roots of all the numbers in the original vector. So if I take the third element of my square root my vec, this is going to work. It's going to give me 2 because the third element in the square root of this vector is, of course, the square root of 4. So it's 2. Lastly, just be careful that some functions that probably you've seen already, meaning R functions, if you feed to them a vector, they might return just a single number. Okay, it depends on which function you're using. So sum is a function that's going to be applied to all the elements of the vector. Okay, so the sum of all the numbers in my vector, of course, in this case will be 20, 6 plus 5 plus 4 plus 3 plus 2. And there's other functions. Okay, so here, this works because sum is an already existing function in R. Okay, same thing. Mean is like the Excel function average. Okay, it's going to compute the average or the mean of whatever you feed it. Okay, here you feed it the vector myvec. Okay, so mean would be 4, of course, because 20 divided by 5 would be 4. And just an example, product. So prod would be for product. So would be the product of all those numbers, in this case, 720. Okay, so this is just for a bit of syntax in R. But now the first thing I want to show you that's very useful in R is that you can create your own functions. So all those functions, prod, mean, sum, square root, they already exist in R. Okay, so you can use them from scratch. But if you want to create your own functions that do some operations that suit your context, you can do that. And let's see a few examples. Okay, so create your own function. How does it work? How does this work? Yeah, I'm going to create a function. The first thing is that you give it a name, and this can be whatever you like. Okay, I think there's some rules that you cannot start with a number, so careful with that. So you can add numbers here. I could put a do2 here if I want, but it needs to start with a letter. So I'm going to call it my.first.function. Okay, very exciting. I'm creating my first function. The syntax is this. You assign to it, so that's the name of a function. Then you assign to it a function. Okay, but this, you see this word is in blue. It's a keyword in R, so you need to use the keyword function if you want to define a function. But then you use the brackets. Okay, careful. This is regular brackets, not square brackets. And then you're gonna define all the arguments of your function. Okay, so a function takes in some arguments and then spits out some results. Okay, so it's manipulating the arguments and then it outputs a result. So here, for this example, I'm going to define a function with 2 arguments. And here, just for giving you an example in the context of the course, I'm going to define just a utility function. Okay, so the utility function will have 2 arguments in this case. Okay, the first one is the wealth. Okay, so you want to find the utility of a certain wealth. And then there's another argument that has to do with the risk awareness of the person. Okay, so you can play with how risk averse the person is, and this is controlled by the second argument. Going back to the syntax, so function brackets here, you're naming the argument. So those I could have given other names. If I want to spell it out, I could have called this argument wealth, the whole world. That doesn't matter. I choose what are the names of the arguments of the function I'm creating. But then, very important, here we have curly brackets. And I open the curly brackets here, I close it here, and the rest, whatever is in between those curly brackets, is the body of the function. So here I do all the operations I want the functions to do. And probably I'm going to make the function return something, and this is done between those curly brackets. In this case, it's a simple function. I just want to return this utility. So this would be the exponential utility. I just want to return this. Okay, because I just want to return this, it's totally fine to just write it, and then R is going to return whatever is the result of this thing. Okay, 1 minus the, so exp is a function already existing in R. It's just the e to the power of blah blah blah. Okay, in general, function, you put the arguments between regular brackets. So here, exponential of minus a times w would just be whatever the user has entered for a and w. Okay, so let's check the result. Now, I need to execute my function so that R recognizes that the function exists. Okay, so if I select everything and I again use the shortcut Control Enter, or I click Run here. Okay, so run the current line or selection. I'm going to click Run. Now here in my console, I have declared this function. So now this function exists because I have created it. Okay, I'm the creator of this new function. How exciting! And now I can use it. Meaning, I can type my first function, which is the function I just created. I give it specific arguments. Then I launch this in R. Okay, again, you can use Run if you want, or the shortcut Control Enter. Here I click Run. Now I get the result of the function, which in this case is just this bit. Okay, and you can do that. Okay, so if I had a wealth of 2 instead of 1, then of course my utility would be a bit bigger. Okay, and if I had a wealth of 5, oh, how wealthy I am, I have a wealth of 5, then this would be this. Okay, and of course, if you change this parameter a, you would get something different as well, of course. Okay. Okay, that's it. We have created a function in R. Obviously, this is a straightforward example, but there's no limit to the complexity of the function you create. And the second, we're going to create something slightly more complicated. Okay, now just if you want to visualize, say what we just done, creating a function that's the function of the wealth on a 2D plot, you can easily do that in R. So I think in the stat class you use ggplot2, which is great. Here I'm just going to use the basic. So ggplot2 is an external package. I'm not going to bother with that. I'm just going to use the basic R here to show the visualization of the utility function. So, but also this is going to allow me to show you an interesting feature of R. I would like to display this function on an XY axis. So X would be different levels of wealth. And then the y-axis would be the utility function, okay? So what I can do is declare a vector of different wealths. Now, this command, 1:30, would create me a list of integer, 1, 2, 3, 4, up to 30. And let's say that this is what I want to do here. I want to display the utility of all of those amounts of wealth, 1, 2, 3, up to 30. So I would create a vector, and I declare a vector that's called x here. So if I do that, whoops. If I create x, then I call back x here. You see that the numbers are there. For the y values, what I want to do is simply apply my utility function to all those x's. Okay, but here it turns out that R works in, I think, a pretty smart way. You can do that like one shot. Okay, meaning if in the first argument, which is the wealth here, I feed to the function. Okay, so this function is very hungry, so I feed it the value x here, but x is a vector, but that works fine. The function will compute the result for every single element in the vector, giving me exactly what I want. Okay, so let's try this. I'm going to just call this in the console, and you'll see with a specific value a here. Now, a is not a vector. Okay, I'm just giving. I want the parameter or argument a to be just in this case 0.25. But x is a vector. So the result of that would be that this is finding the utility function of the first number of x, which is 1, utility function of a wealth of 1 with the parameter a equals to 0.25. Then the utility if the wealth is 2, and of course a is again 0.25, that doesn't change, and so on. Okay, let's just double check that this indeed works. If I just put the wealth of 1, you see I get the same number as I had here. Okay, and a wealth of 2, I get the same number, 39, as I had here, and so on. Okay, so here I'm just saying that there's a convenient behavior that you can feed to this function you've just created, a vector, and it's gonna find in one shot the 30 values evaluated at each element of the vector. And now this allows me to use the function plot. So first, so here there's a few arguments. Let me explain them in a second. If I just type plot xy, this is going to work. It's going to show a graph of all the values x on the x-axis and all the values y on the y-axis. Okay, I haven't declared, I'm a noob, and I haven't declared y here. So let me just declare it. Okay, now by declare, I mean telling R that y exists and y should be exactly those values. Okay, now that I've done this, using the command plot x, y should work. Okay, here, let me make so on the right, as I said, you will have, so here there's a few different windows, but here, I don't care about packages. So I'm just going to open the plot one, and you see this is the plot of what I wanted. The y value, which is the utility as function of x. And here, of course, it's a concave utility function. Now, I don't want to spend too much time on visualization, but you can improve the display, a little bit by just a few tweaks to the plot function. Okay, which are those things. I want the type to be line, so L for line. I don't want to see points. I want to see a line. Then I'm going to give it a color. Okay, my favorite color in R, it's personal to me, is brown number 3. Okay, and then LWD would be the width of the line, And then here, sex.lab, I'm just making the labels a bit bigger. Okay, so if I launch this, you see it's, in my opinion, slightly better. It's a nice line. It's, it's a nice kind of almost red color, but it's not red. It's brown number 3. Okay, you can Google all the R colors and find your favorite. And then that's it. Okay, so I think that's the kind of a basic thing, declaring a simple function and maybe plotting if you want to plot the result. Okay, now let me just do it again with a different A, just to show you that A just controls how kind of strongly concave the function is. So if A is small, you'll see that it's going to be more similar to a straight line, so the person will be less risk averse. Okay, so if I do it again with a smaller A, you see it looks like more like a straight line. And if A is very, very small, it's going to be pretty much a straight line. Okay, I think that's it for that. Now, just another few examples of creating functions that are relevant to us aspiring actuaries. So, for example, you could create a function that returns the present value of an annuity. Okay, so let's do that. It's not too complicated. I want the present value of an annuity. By annuity, I mean a certain annuity. Okay, there's no mortality here. So just the present value of payments of 1 every period for whatever number of periods. In that case, an argument we need to have in our function is n, okay, the number of periods. The interest rate, I. Okay, again, I use the same notation. Okay, I define annuity.pv to be a function of an argument n, an interest rate. And lastly, arrears will be a logical or Boolean value, okay, true or false. Okay, so arrear would be true. Well, if I set arrear to be true, it means I want the present value of an annuity in arrears. Okay, the payments happen at the end of the period. If I set arrears to be false, then it means I want the present value of payments in advance. Okay, the first one happens right now. Okay, now I open the curly brackets, meaning that here I'm going to define what I want the function to do. Okay, first thing, this is not entirely necessary, but just to break down this in 2 steps to show you that you can do many, many steps in a function, I define a discount factor to just be 1 over 1 plus I. Okay, or if you prefer, I could have written this as 1 plus I to the minus 1. Okay, this would be exactly the same thing. Careful that just here, if you were to type power of -1, this wouldn't work. You really need to put the brackets. And then with this discount, so here I have declared discount inside the function. Okay, just a small comment: discount does not exist outside of the function. Okay, so let me just declare this function. Now the function exists, but if I tap discount, it doesn't exist. It doesn't, R doesn't recognize it because I've declared it inside the function. Just a small detail that probably good for you to know. But anyway, coming back to the what I'm doing in my function, I'm just creating the present value of an annuity. So we have a function from the financial maths part of the course. We know this is just 1 minus the discount factor to the n, divide by I. Okay, let's start with this. Okay, for now, I'm going to delete this. Okay, 1 step at a time. Okay, and now, because, careful here, I define value here, okay, which is just what I want, present value of the annuity. If I want my function to display this, I need to use return value, okay? And in general, I would encourage you to do this. When you have a complex function, break it down in steps, and then at the end, use the explicit command return to return the value. This is not mandatory in the sense that, if you recall, here I did not use return. Okay, I just did the calculation, and if I just do the calculation, R is going to return. Okay. However, I think it's good practice to explicitly tell R what you want to return. So this would have had the exact same effect. Okay. Well, actually, but there is a difference. So as soon as R encounters the command return with whatever, it's going to return this, and then it's going to stop doing things. Okay. So that's maybe something you should be aware. If I use return and I do other things, okay, now I don't know why, but I would like to compute the square root of pi, okay, but R is not gonna do the square root of pi because it's just gonna return whatever is here. It's not totally ignore what I've said afterwards. Okay, but again, that's just maybe a side note. Okay, if I keep going, sorry for jumping back and forth, but I want to go back to my annuity function. Now, let's just try it. Okay, so if I launch this, I'm going to use the function annuity.pv. I'm going to give it a specific term, and I'm going to give it a specific interest rate. Okay, now you could double check with your calculator that this works. Hopefully it does. Let's just try it again. If I give it smaller interest rate, maybe just 1%, then it should be a higher value because I'm discounting less. Okay, and in the limit, if I give it a interest rate that's very, very close to 0, then I should get the value 10 very closely, or close to 10. That's all good. But now this, I'm not using, you see, I'm not using arrears here because I've deleted the part where I was using arrears. What you can do, if you want to create a function that is going to return the present value in arrears if arrears is true, or in advance if arrears is false, is you can add this little bit that I had deleted. Okay, but this is using a new command, if else, which we should probably explain. It's not too complicated. If else is a function in R. It's going to look whether this is true or false. If it's true, the result of if else will be the first value here. Okay, and if this thing is false, then the result of the if else function will be whatever is in the third argument. This works really like the if function in Excel. Okay, so this is a condition that can be true or false. If it's true, then the result of if else will be whatever is in this thing. If it's false, then the result will be whatever is in the third argument. Now, this is what I want in this specific case, because if arrears is true, then that's the answer. Okay, I don't need to multiply by anything. So if arrears is true, that's the answer. So I want to multiply by 1. Okay, of course, multiplying by 1 has no impact. However, if this thing is false, then I want to multiply the value by 1 plus I, because remember, the payments are in advance. Okay, the first one happens right now. Then the present value of the annuity is multiplied by just 1 plus I. Okay, so this has the effect I want. If the user has entered here true, okay, then the result should be multiplied by 1 plus I. Okay, so let's try this. Okay. Okay, arrears true, that's exactly what I had before. But then arrears false, then I'm going to get something bigger because the first payment happens immediately. Okay. Let's just try something. Well, I mean, okay. If we're in arrears and I multiply this by the interest rate, in this case 10%, okay, then that should give me exactly the value of in advance. Okay. Okay, that's another function. Now, just lastly, let's do one more example of a more complicated function. I say lastly, but there's another thing I need to talk about after that, and probably I'll do another video for that. But one more example of a fairly complicated function, or more complicated function, would be for us to find here the accumulated value in a superfund balance. Okay. Now, this is not overly complicated, it's just longer. What I want to do here is implement this big formula we had in the lecture slides of week 4 for the accumulated value in the superfund of someone based on many different parameters. Okay, let me just for a second share the lecture slide just to show you what I mean. Okay, if hopefully this works. What I'm trying to share to implement is this big formula we had towards after a couple of slides in of the week 4. Okay, so this is the week 4. We started by slowly explaining that okay, you can have a tax on contribution, you can have a tax on investment income, you can have a blah 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 investment management fee, and so on. And at the end, as we complexify the situation, we got to this kind of bigger formula where this would give you the accumulated value in the account after n years if there's increasing salary increase of F per year, and et cetera, et cetera. Okay. Now, this is a simple formula. It's just longer, and I'm going to implement it in R. Okay, so back to R. It's quite handy that I've done it already, but maybe you can double check in real time that you agree with this. But the accumulated value in my super would be a function of many things. Okay, just to go quickly over this. S was the starting salary of the person. N is the number of years after which I want to find the accumulated value. F was the rate of increase of the salary. Superannuation guarantee rate was 12% in the lecture. Now, actually, this is something I should have explained maybe before, but I'm going to explain it now. It's the same. Here you see I haven't declared this to be anything by default, but you can declare the argument to take a default value, meaning that if you don't specify the value when you call the function, then R is going to use the default value you have provided. Okay, let me just go back to the annuity example. Let's say that I had entered a default value of n equals 10, and this I a default value of 10%, and then arrears value by default of true. Then, when you do that, you could just call this, just call the function without any arguments, and it's still going to compute this. Well, yes, it's going to compute whatever the result should be for the default values. Okay, so but of course you can still use the function in a more general way, meaning if I call this for n equals 20, now it would compute the annuity present value for n equals 20, but still an I of 0.1, which is by default, and still in arrears. Okay, but if I enter n equals 20, but arrears equals false, then I would be getting something different. Okay, this is just telling you that if when you declare the function you put some values here, R assumes that those are the default ones. If the argument is not specified, it's going to use those. Okay, so by default, I would put the tax on contribution to be 0, the investment tax to be 0, the management fee to be 0. Okay, by default, I'm going to put the 8% gross interest rate, as we've done in the lecture, a fee of 0, an inflation rate of 0, and I wanted this arrears, in this specific setting, what I call arrears is if the annual flat fees are paid in arrears or in advance. So I put in arrears to be true by default. Okay, I do this in a few steps. What I call NI here is the net interest rate. Okay, in the lecture slides, we saw that this was just the gross interest rate times 1 minus the tax minus the investment management fee. With this net interest rate, then I can compute my big formula. The accumulated value will be this. Okay, you can double check that you agree this exactly corresponds to the formula we saw in class. The only okay, this is the formula we saw in class, but here I complexify it slightly. I do the same trick again. Okay, so if those fees, those flat fees, okay, insurance fees or just admin fees, are in arrears, then this is exactly like we saw in class. So I just multiply this by 1. But otherwise, if arrears is false, so those fees are in advance, then we should multiply them by 1 plus the net interest rate. Okay, this is exactly the same trick as we did here to consider the possibility that those fees might be in advance. Okay, that's the accumulated value. And then lastly, I to find the value in today's dollars. So this is the very last thing we saw in the lecture slide. Let me jump back just to show you. Okay, so thus far I've implemented this formula, but I've also allowed the possibility for those fees to be in arrears. But then after that, we considered the inflation. Okay, so with inflation, if you want the result in today's dollar, you just need to divide by the inflation rate to the power of the number of years in the future. Okay, so this is just what I'm doing. Dividing like this: 1 plus inflation rate to the n. Okay, now, so I'm finding the accumulated value in today's dollar, and then at the end, as I said, I return explicitly. So I tell R, return please, whatever this is. Okay, so let's try. So here, first thing, again, I need to declare the function. I need to tell R, okay, this is the function I define. And by the way, if we want to see what you've declared so far in your R session, okay, you can do this and go in this window called, I believe, environment. Okay, so in environment summarizes. Okay, so far my vec exists in my current R session. Okay, so my vec, if I want to recover it, I can just type my vec. Okay, and I've declared the function accumulation super and etc. So those things, R just tells you, okay, those things exist now. You can, you can use them. As a comment, if you close your R session, okay, you can save your R script. Okay, that saves the script. But those objects on the right that you've declared, they would disappear though. Okay, you would need to rerun your R script in order to recover those values. Okay, let's just try the function. This is really just refining the values I found in a lecture for week 4. Okay, so if we don't consider anything, this was the very first value we computed. This person, ignoring all taxes and fees, they would have 4 million in their super. But then you use the function, and increasingly you specify the arguments. Okay, so if the contribution tax rate is 15%, then their super is now just 3.4 million. If we put an investment tax rate of 15%, now they have 2.5 something million. If there's now an investment management fee of 1%, then we go down to 1.97 million. If now there's a flat fee, insurance and admin fees every year in arrears of 500, we get this. And lastly, if you want this in present dollar, meaning we would consider an inflation rate of 2%, then we would put 2% for inflation rate. And then we get this value, 803K, which should match exactly. Let's just go back to memorize this number, 803K and $395. This should match exactly what we found in our lecture. Okay, yes, it is this number that, of course, we had computed either with a calculator very tediously or maybe in Excel. But you see in R, you can do those things. And now that you have this function you've declared in R, of course, because it's a pretty general function, you could reuse it later, right? Or maybe you can use this to double check your calculation when you do the tutorials, and so on. Okay, I believe that's enough for one video. Now I have a few more things to cover. I'm going to cover for loops, and then I'm going to cover simulations in R, and then we're going to do one more slightly more complicated example, but an example of a problem we've dealt before in tutorials. But now I'm just going to redo it in R. I'll do that in a separate video. Okay, so bye-bye for now.